So we'll continue our discussion on the semantics, more specifically the operational semantics of Poisson values. And this is something that we're going to pick off from our last module. We started discussing the operational semantics of the Poisson value and said, what are the possibilities if I add to the Poisson value, or if I divide by the Poisson value or from the Poisson value, and so on. So overall, the problem is that we need to define the operational semantics. And while we looked at one or two examples in our previous module, we are going to study this topic in more depth in this particular module. And the guiding principle in defining the semantics for the Poisson value is that, notice that if a Poisson value has been generated, that basically means that the original program had UB, right? Because if we are lowering something like a source language like C into LLVM IR, then if LLVM IR is generating Poisson, then the original program must have been generating undefined behavior, or must have been triggering undefined behavior. And we just decided to generate a Poisson value instead of actually triggering undefined behavior, so that I can do more transformations like hoisting and other things. And so if a Poisson value has been generated, that indicates that there was UB in the original program. And so any choice for semantics is okay. I mean, from a correctness point of view, it doesn't matter what I choose. I can choose, for example, that a Poisson should be converted to some random value or something like that, and that would be okay. Because after all, generation of a Poisson value already means that the original program had UB. And if the original program had UB, then anything is okay. Basically, the program was illegal. But we want to pick a choice which maximizes the optimization opportunities. As we have discussed in the past, the IR designer needs to basically carefully walk a tightrope between optimization opportunity in the source and the optimization opportunity thwarted because of the UB semantics in the destination. And that was the whole motivation of introducing Poisson values. So let's take an example. So let's say I have this opcode in my IR level, which looks like add NSW, which NSW signs no signed overflow. And then there is this constant, and then I add one. Now the NSW keyword is important because this basically means that if there is an overflow, then it returns a Poisson value. All right. And in this particular example, assuming it's a signed integer, 7 FFFFFFF is basically int max in my 32-bit representation, and if I add one to it, that indeed triggers overflow. And so what gets returned to P is not 8 and 7 zeros, but what gets returned to P for this particular instruction would be a Poisson value. And that's because of NSW. If, for example, I remove the NSW, then this becomes a regular add with a wraparound semantics, and that would basically mean that this becomes 8 and 7 zeros and things like that. And then let's say I basically start using this Poisson value. So let's say I subtract 1 from the Poisson value, or I add 0 to the Poisson value, or I OR the Poisson value with 1 and things like that. And the question is what do I get on the left hand side? And I'm deliberately naming these variables or registers as P2, P3, P4 to basically indicate that all these operations will also yield a Poisson value. So irrespective of what the other operand is, for example, if I do P minus 1, that's just going to lead, if P was Poisson, then P2 will also be Poisson. If I do P and 0, now notice that when I say P and 0, you may be tempted to say, oh, anything ANDed with 0 is just 0. But actually anything ANDed with 0 is, in this case, is not 0, because the Poisson value ANDed with 0 returns a Poisson value. So that is slightly counterintuitive, because you would imagine that with 32-bit integers, if you AND with 0, then you should get a Poisson value, you should get 0. But if you AND Poisson with 0, then you get a Poisson value. And I'm going to show later that it's a good idea to actually return Poisson in this case, rather than returning 0, because Poisson actually gives you more flexibility. A Poisson value basically means that it should never be used in the future. And so, you can always replace a Poisson value with 0, because after all, if it was never going to get used, then how does it matter whether it was 0 or 1 or 2 or 3 or whatever? And so it's always okay to replace a Poisson value with 0. And keeping it Poisson is basically a good idea because it gives you more flexibility when you talk about optimization. Similarly, let's say I do OR I32P1. Now P is poison in this case because of this, but when I'm ORing it with 1, you can say, oh, the last bit will always be 1. The least significant bit would always be 1, but we don't, that's like, we don't really track that. The operational semantics that an IR like LLVM uses is that if you OR anything with poison, you get another poison value. So all these values, you started with a poison value because of this operation, and then any operation from these kind of operations also return a poison value. P2, P3, P4 are also going to return poison values in this particular example. So why did I choose these particular semantics? I could have chosen any other semantics. For example, I could have said that if you add 1 to poison value, then it's undefined behavior. Alternatively, I could have said that if you AND 0 with a poison value, then either I could have said it's undefined behavior, or I could have said it always returns 0. But I'm choosing my semantics to maximize the optimization opportunity. If I choose AND of P with 0 to be undefined behavior, that basically disallows me from hoisting that particular instruction above, because now I have to be very careful, because this particular instruction would now cause undefined behavior. Whereas if I just say that it returns a poison value, that's just saying, okay, I can generate this value speculatively, and if I don't use it, the program would still be okay, equivalent. The two source and target programs would be equivalent. Similarly, why not just say that AND of poison with 0 is 0? Why do we want to keep that AND of poison with 0 is poison? Because poison value, return value, gives me more flexibility. A poison value is an error value, which basically says that this value should never be used. If I force it to be 0, then in some cases I may want to kind of just change it to 1 or something like that, but I'm not going to be able to do that. So keeping it poison is actually keeping more flexibility intact, and if you have more flexibility, you have more space for transformation, and thus more optimization opportunity. So anyway, because we have generated a poison value, if I'm operating on a poison value, irrespective of what the operation is, as long as it's not a dangerous operation, as we're going to look at what are dangerous operations later on, we just return poison value, and that's a conscious choice to maximize optimization opportunity. Now let's look at a slightly more difficult operator, which is the branching operator. So what if there is a conditional branch, like an if then else, or in a 3 address code IR, it would look like branch equal to or branch not equal to or something like that. But overall, basically the idea is that if some variable P, and this P could potentially be a poison value, then do this, else do this. Now, because this is a poison value, you could have said, there are multiple options here. You could have said, I'm going to assume that poison value can take any of the branches. If you try to branch on a poison value, then any of the branches can be taken non-deterministically. But that is a little bit, there are examples where that would cause difficulties in optimization. The other option is, if you branch on a poison value, then everything that is in the if and the else block is basically becomes poison also. But that again becomes really hard to track, because there are memory operations, there are stores and loads. What do I mean by saying that everything that is generated in the if block and the else block become poison values? Once again, I'd like to point out that if I'm doing this operation, it already and this value was a poison value, P was a poison value, that basically means the program has already exhibited undefined behavior. So I'm really free to choose any semantics in this case. But I'm trying to choose semantics that are first easy to model, and second, maximize the optimization opportunity. Now let's look at another example. Let's say I say x equals int max, and this y equals x plus 1. So here y will definitely be poison. And then if I say if y equals 10, then something something. So firstly, I'll say, I'll do a comparison operation between y and 10. And if y was poison, then the comparison result, which would be a Boolean value, would also be poison. It would not be neither false nor true. And then when I branch on a poison value, then I would have to use the semantics of whatever I want branch on poison to be. Here's another example. I just basically have some arbitrary expression x equals ... I don't know whether x is poison or not. And now I just branch on x. And now I have to worry about the fact that x may be poison. And the question is, what should I do if x is poison? Now, I'll give you an example. Let's say if I say that if X was poison, then non-deterministically one of the branches is chosen. And in my compiler analysis, I was able to figure out that X is either 0 or poison. Then if my compiler analysis has told me that X, by 0 I mean false. So if the compiler analysis has told me that X is definitely either false or poison, then I would basically say, okay, let's get rid of the if block completely and kind of just get rid of the if condition and just execute the else block. But if I use the non-deterministic semantics for poison value, then that basically means that the program can actually also execute the if block, because poison can cause the if block condition to non-deterministically choose either of them. And so that doesn't sound like a very good option from an optimization opportunity perspective. So what is typically chosen? The easy option, and the one that is actually chosen by an IR like LLVM, is that whenever there's a branch on poison, you declare that to be UB. So if there's a branch on poison, then you declare that to be UB. And that's basically going back to kind of the C semantics, saying, okay, I tried to kind of contain my error so that I could do hoisting optimizations. But as soon as you try to kind of do some complex operations like branching on the poison value, then that's just UB, which means that it should never happen that you try to branch on a poison value. And if you do that, then many of your optimizations become valid. So for example, if I look at this example, if I say X equals some random value, which could be poison, and say if X, then this, else this, if my compiler analysis has been able to figure out that X is always false, then I can completely ignore the poison value, because if X was poison, then this is anyway UB, so I can do anything. And now it becomes okay to completely get rid of the if block using dead code elimination and just execute the else block. So that's the easy option that an IR uses. Branch on poison triggers UB. And so basically, these IRs like LLVM has this keyword called unreachable. So there's an instruction called unreachable. If the unreachable instruction basically means that this point of the program should never be reached, or the compiler can assume that this point of the program will never be reached for all legal inputs. So what I mean by saying that branch on poison triggers UB basically means that I can kind of replace this whole block with the unreachable statement if I'm sure that P is poison. If I'm not sure that P is poison, then I can kind of assume that P is not poison, because if I'm branching on P, then it is only legal to branch on P if P was not poison. This is similar to how we discussed undefined behavior when we were talking about the source language. Now, although this is an easy option, which is branch on poison causes UB, it causes some loss of optimization opportunity. And this is something that, as I've been emphasizing, a designer needs to walk a tightrope between optimization opportunity and thwarting of optimization opportunity. And this is a choice that LLVM designers have had to make. And I'm going to show you a couple of examples where this actually is not such a great choice from optimization opportunity, but we have to live with it. And here is an example. So let's say if I say if A, then I say, inside if A, I say if B and then something, then can I transform this into if A and B, which is this double ampersand operator represents the logical AND operator. And the answer is no, because consider the case when B is poison and A is false. In the source program, the first if condition is just going to say if false, and it's never going to execute if poison, right? But in this destination program, in the target program, I'm going to say A and B, because A is false and B is poison. A and B is going to give me poison. And now I'm going to say if poison something, and that's just going to trigger UB. So for this particular input, when B is poison and A is false, the source program is well defined and it basically does nothing. And the target program triggers undefined behavior. And so this becomes an illegal transformation. In general, because branching on poison is undefined behavior, it is not okay to hoist such instructions that branch on poison. So in this case, I'm trying to hoist this if B and kind of merge it with if A, right? An alternate kind of transformation that I could have also used for this example is if B, if A, and then ... right? And this would again be illegal because once again, I can't hoist the branch on B before branch on A, because if the branch on B was actually causing UB, then in the source program that UB is caused only conditionally, that is when A is true, whereas in the target program that UB gets caused unconditionally, and so they don't remain equal. And this is a price we have to pay at the IR level. Why are we paying this price? Because we want to kind of restrict our transformation space to such that the transformations are from the same IR to the same IR. If, for example, we were allowed to use different languages for transformation purposes, then it would have been much easier. But if I use different languages, then my compiler pipeline design becomes even more complex. So we want to have the same IR, and we want to have lots of transformations that does two IR to IR transformations. And that basically means that I have to choose some semantics for my IR for error conditions. And when I choose those semantics for my IR, then I sometimes have to sacrifice some optimization opportunity. Here is another example called for loop unswitching. So let's say I have a loop while C if D S1 else S2, and I want to hoist. I want to kind of do loop unswitching. So basically, I want to hoist the check of if D, and assuming that D is basically loop invariant, then I can do if D at the very beginning and say while C S1 else while C S2, right? So this is basically the transformation I want to do. And if in the absence of Poisson value, this transformation is actually a legal transformation. It's a very useful transformation because inside the loop now we are avoiding a branch, right? Inside the loop is going to be executing most of the time, and in the target program we are avoiding a branch. But when I look at this particular transformation, if I look at the Poisson semantics, then if D could be Poisson, if D was Poisson, then and C was false, then this transformation is wrong, because in the source program would never enter the loop if C was false always, and so the source program would never enter the loop, and so the program would be well defined. Whereas the target program, because D was Poisson, is going to straight away trigger undefined behavior, and so this transformation is not correct. It's because for inputs D equals Poisson and C equals false, they don't yield the same behavior. Alright, so that was branch on Poisson. Now let's look at some more examples of operators related to Poisson value. So what if I store a Poisson value to memory? So I say star x equals p, and let's say x I know is not Poisson. Then if I try to load from the same address, star x, then what do I get back? Alright, firstly, are these supposed to be are they well-defined operations, or do they trigger UB? And if they don't trigger UB, then what are the values that are getting returned? So here, this is actually an easy case, and the answer is that basically when you store a Poisson value to a certain address, where the address is not Poisson, then you're basically setting the memory bytes corresponding to x to the Poisson value p. And then if you load it back, then you get the Poisson value back. So if you say p2 equals star x, and the last time you stored a Poisson value to x, then whatever is the last value that you stored is get kind of loaded back because of memory semantics. And so what you will get back is the Poisson value back. Notice that I'm talking about the operational semantics here, and which is the runtime operational semantics of what happens if the Poisson value is stored, and then later on at some later point the same value is loaded. What is the value that I should assume I have got back? And I'm saying that a Poisson value is stored to the memory, then you remember this fact that at this particular location the Poisson value was stored, just like you remember any other value. Poisson is no different, and then when you load it back, you get it back. But what happens if you try to store to a Poisson pointer? So let's say this p was actually potentially Poisson, and let's say it was and I say star p equals x. Now if p was Poisson, then this becomes a big problem, because Poisson basically means it was an error value, and so the error value, we haven't been keeping track what the error value is. It actually triggered UB. And that's why we generated this Poisson value, and now I'm trying to dereference it. So what should I really have semantics for? And the easy option, once again, just like we had the easy option for branch on Poisson, the easy option for storing to Poisson pointer is that this also triggers UB, because we don't know where to store. And so we just take this easy option. Once again, whenever we take an easy option that something triggers UB, we pay the price. We pay the price that this particular such instructions can now no longer be hoisted, because if they trigger UB, then you want to make sure that the target is not going to trigger UB in cases where source would not have triggered UB. Similarly, if I try to load from a Poisson pointer, so if I say x equals star p, once again because p is Poisson, then that would also trigger UB. Just like store to a Poisson pointer triggers UB, a load from a Poisson pointer also triggers UB because the pointer itself is an error value, you don't know where to load from. Finally, we have this is an example that we have discussed in the previous module. If you try to divide by a Poisson value, even that triggers UB because you have to conservatively assume that the Poisson value could potentially be 0. And so y divided by Poisson value is also something that triggers UB. And that's something that we've discussed in our previous module. Okay, there are consequences to these decisions. So if I say x equals star p and star p could, p could potentially be a Poisson value, then it's not okay to transform this to, to hoist this x equals star p, this memory access above the loop, if it was loop invariant. And this becomes illegal because now in the original program, this, if p could have been Poisson, then I wouldn't have executed this statement that triggers UB in the source program if the loop was never entered. Whereas here, irrespective of whether the loop is entered or not, x equals star p is going to trigger UB. I want to point out that this is different from, let's say, saying x equals an. So here I was actually dereferencing a pointer that could potentially be Poisson. Now let's look at another example. Let's say A was an array which was 256 bytes, and I know my compiler analysis was able to figure out that n is between 0 and 256, right? So which means that n belongs to the range of A. Now when I do that, then if I say an, then basically this an is nothing but star of A plus n into size of int. So let me just assume that a size of int is 4. So this just becomes star of dereference of a plus n into 4. Now the good thing is that a plus n into 4 is not Poisson, all right, because this I know is basically belonging to this address range, and this is perfectly okay. And so this case is not the same as saying x equals star p, because here p was known to be not Poisson. So p could have been Poisson in this example, but here we know that an or a plus 4 into n is not Poisson, and so here it is actually okay to hoist the computation and say x equals an can be brought up above, hoisted above using loop invariant code motion above the loop. And this would be okay because the compiler has been able to determine that the access an, the memory access an, the pointer is not a Poisson value. Notice that it is still possible for the value that was read from an to be Poisson. So x can still be Poisson, right? The pointer should not be Poisson, but the value that was returned can still be Poisson, and yet this transformation this loop invariant code motion transformation would be legal. And so we already seen how a memory load or a memory store can have constrained motion. There are some more examples like divide by 0. So let's say in my loop I have x equals y by z. It's not okay now because y by z, if z could potentially be Poisson, then I cannot just basically hoist x equals y by z above the loop, because y by z can potentially cause undefined behavior, can potentially trigger undefined behavior. If you contrast that with integer overflow, so for example, if I just change the divide operator with plus operator, then it becomes okay, right? So plus is okay, but divide is not okay. And this is on purpose because division on many architectures basically causes actually an exception, whereas a plus is silently ignored using wraparound semantics or saturating semantics or something like that, and the value is stored in the destination. So some opcodes have constrained motion, and some other opcodes like addition, subtraction, multiplication, etc., or other logical operations don't have constrained motion. And these are basically conscious design choices made by the IR designer. Finally, I would like to point out that a Poisson value is a non-deterministic value. It's an error value. Basically means that if a Poisson value was generated, then I'm sure that the program triggered undefined behavior. And if the program triggered undefined behavior, I could basically do anything. And so it is always okay to determinize a poison value. For example, if there's some program which basically generates poison, for example, by adding int max, adding 1 to int max. I'm just writing it shorthand for x equals poison. Or there's nothing like poison. There's no poison value typically in an LLVM, in an IR like LLVM. You just basically generate poison values by using some particular operations like addition to int max, addition of 1 to int max. But then it is always okay to kind of change this to, let's say, a deterministic value, let's say 10 or 0 or whatever else. Because after all, it's a poison value means that's an error value. It should never be used for branching. It should never be used for divide by, as a denominator of a division operation. It should never be used as an address of a memory access. And so because it is pretty much never used, and anywhere it is used, it just propagates the poison value, which means it just creates more poison values. You can always kind of change that to some deterministic value 10, and that would just mean that you have reduced your optimization opportunity because you basically picked one deterministic value, but that is not illegal from a correctness point of view. So it's always legal to determinize a poison value. Here's another example. Let's say y is some value, and then you figured out that x is poison. Then the compiler is well within its rights to change x equals poison to x equals y. Compilers will typically not do this. I'm just using these examples to illustrate that it's okay to determinize poison. Poison basically is a non-deterministic error value, and so it's always okay to do this. These are not real examples that compilers do, but they are well within its rights to do this if it requires to do this.